Hello there, Module 10, an Introduction to Simple Linear Regression. You'll have to pardon my voice. I've got a little bit of a cold here or allergies, so you may want to auto-tune your audio there. But in regression, we are attempting to describe a relationship between two or more variables through a particular mathematical model. All right, that's the big overarching theme of regression. Simple linear regression attempts to describe a relationship between two variables using a linear model. Okay. Now, once a model is obtained, it can be used for two things. One is prediction. That is a reference to future values. What could we see for a particular variable? Or it could be used for explanation. Okay, and that's a reference to current or past values. In other words, for what we have seen so far in our data, if we change one of the variables by a certain amount, what kind of changes would we expect to see in the other variable? Okay, so prediction and explanation. I forgot the I here in explanation. All right, so simple linear regression. Let's motivate this with an example. Suppose here that Y is the age of a sparrow and X is the corresponding sparrow's wing length. Can we describe the relationship between those two variables? Is it linear, this sort of thing? So here's some data we have for 13 sparrows from ages 3 to ages 17 and their corresponding wing length in centimeters. And here is the scatter plot of such data. Okay, this is called a scatter plot here, and it maps the paired data there. Does there appear to be a relationship when you look at the scatter plot? Yes, it does. There does appear to be a relationship. In fact, it appears to be linear, pretty linear there. And there's my attempt at a good line through the data. We'll get it more precise later on, but it does appear linear. So what we'd like to do in general, not necessarily just the sparrow data, but in general, regression wants to find an appropriate linear relationship given data on X and data on Y. Okay, and it does so with the following model. So I'm going to up front here define the linear model, the regression model that is used. Now, Y sub I is defined to be the response of the ith subject Sometimes it's called the dependent variable. So if you look at our sparrow example, the response, the way we have it modeled, is the age of the sparrow. And X sub I here is often called a covariate, and it's usually known. And in a modeling or data situation, it's something that you would be able to identify and hopefully use your model to try to guess at what the corresponding response is. So it's called a covariate of the ith subject. Sometimes called the independent variable, or sometimes called the predictor variable. Okay, and so for our sparrow problem, the wing length is our covariate or our predictor variable or our independent variable. I'll use those those ideas interchangeably. Response, predictor variable, this sort of thing. Okay, and this is for I going from 1 to n. Clearly I've got n equal to 13. I think it's 13. Yes, 13 pairs of data there. Alright, so what we do is we model the responses as follows. So the responses are modeled by the following: yi equals beta naught plus beta 1 xi plus epsilon I. Okay, so we're saying that y is related to x through this stuff, which is the form of a line. If you remember back from your high school math days, you probably had this as the equation of a line, mx plus b. We're representing the line a little bit differently here, but this is still the line part of the model here. Beta naught plus beta 1 x, and this term here, beta naught, is the intercept. It's called the intercept. Beta 1 is the slope. It's the coefficient in front of the x. And this epsilon here, epsilon I, is called an error term. Okay? And so what we're doing is we're saying that y is related to x through the simple line, but then plus some error term. Oftentimes this is called a deterministic component, and this is called a random or error term component. It's the reasonable part of the model that says, hey, yeah, y is related to x through a line, but there's also some variability in the data, and this tries to account for that variability. Okay, a little more about the error terms. In simple linear regression, we assume that the error terms, that's epsilon I, are distributed normal with a mean 0, and the variance is sigma squared epsilon, and this is for all I going from 1 to n. And we also assume that the error terms are independent of each other. That is, they don't affect each other. Okay, so this is the mathematical model assumption that's set forth. Y is related to x through a line plus an error term. If we want a picture of this, this is a picture of the population model. We would have x here as a horizontal axis, y as the vertical axis, and there's a line that relates y and x, and this line is beta naught plus beta 1x. That's the line, but in reality the scatter plot would not be something like this, where all the data is on the line. If you look at the scatter plot for the sparrow data, that's not reasonable there. We want instead, let's see here, the data the data would bounce off of the line, something like that. And so excuse me, the amount that it bounces off of the line is modeled according to the normal distribution, this error term here. And so for a given x, we have a normal distribution that tells us how much the y value might bump off that line. Okay, so I'm trying to draw these normal distributions. They're all the same. The only thing that's different about them is their mean. Their variance is the same, but the mean is different. You can reference your book for a much better picture of that scenario. But this is our model designation, and The overall assumptions in the model are, there's 4 of them, and they're inherent with what I have stated in here. Okay, and these are the 4 assumptions for simple linear regression. One is that we have a linear model, that x and y are actually related by a line. Okay, and 2, that we have normal error terms. And 3, that we have independent error terms. And fourthly here, that the error terms have a constant variance across I. Okay, and so that's reflected in the first assumption here. There's the linearity part. The normality here is that the error terms are normal. The independence is expressed here, that the error terms are independent, and that the error terms have a constant variance across all I is expressed in that part there. That the variance of epsilon I is sigma squared epsilon. We're going to talk about ways to estimate that later, but that's the variance of our error terms, and it's constant across all the values I there. Okay, now when we think of this model, this is a population model. That is, the beta naught and beta 1 in the model, and the sigma squared for the variance, or the sigma squared, the variance of the error terms, those are all parameters, those are all unknown. And so what we have to do, just like any statistical problem, is we have to estimate our parameters using data, and that's what we're going to do here. Okay, and this next page we're going to look at how do you come up with an estimate for the intercept, which is beta naught, and an estimate for the slope, which is beta 1. So the motivating question here is, given sample pairs for I goes from 1 to n, what are appropriate estimators for beta naught and beta 1? We're going to use an approach called the ordinary least squares approach. And I'm going to set up a picture here to kind of motivate this approach. And hopefully at the end of it you'll see why it's called the least squares approach. But if you think about in a simple linear regression setting, we're going to have a scatter plot. And I'm just going to put a few points here, there. So I've got 4 points there. I've got the horizontal axis x and the vertical axis y. And what we would have would actually be, so this point, say, would be x1 comma y1. This would be x2 y2, and so forth. Now what we're going to have here is, in some sense, a line of best fit that's going to go through the data. And I just drew the line in there. The equation for this line is going to be given by y hat. Okay, and y hat, we're going to call these the y hat values, or the line there, we're going to call that the fitted values. That's the name for it. It's the fitted values of the response that's given by the line. And this beta naught hat and beta 1 hat, these are our estimators. Okay, and when we establish those, that gives us the line. So the question here is, what should we put in for beta naught hat and beta 1 hat? What are appropriate estimators to ultimately give us this line of best fit? Now, what we're going to do here is we're going to set up this thing called a residual. And so I'm going to call epsilon 2 hat, well, let me back up. Let me call epsilon I hat, these are called residuals. Now epsilon I, you remember from the model, is the error term here. Epsilon I hat is our best guess at what the error term is, because what I have in this situation is sample data. I don't have the entire population there. So this is my best guess at what the error term is. And anyway, so these are called residuals. And so just to make a note here, I'm going to call those residuals. Let me define them for you. Let me define one in particular for you. Epsilon 2 hat is defined to be y2 minus y2 hat. And so it's actually, the residual is the difference between the line and the data point via the response. In particular, if I had this is not a point now from the sample, but I can give this coordinate pair the value x2 y2 hat, and the difference here would be that distance there in some sense is the residual. And so the residual is defined to be the response minus the fitted value. That is what the model says the response should be for that given x value. Okay, and we could go a step further. That's the observed response minus the fitted value would be beta naught hat plus beta 2 hat times x2. That's the residual. And so the least squares approach, what it does, in some sense it says, okay, if you want to find a line of best fit, let's minimize the distance between our line and the data. Now what do you mean by distance? Well, for us, distance it can be defined in a number of different ways, but the distance measure that we're going to look at here is going to involve these residuals. You want these residuals in some sense to be small. Well, we can minimize this the squared residuals and the sum of the squared residuals, and so we want to get to that point eventually. Let me write out kind of what I said here, that the least squares approach attempts to find beta naught hat and beta 1 hat that minimize the distance between the data points and the line. Okay, in particular, OLS finds the values of beta naught hat and beta 1 hat that minimize a function. And your book uses this notation. SS, that stands for the sum of the squared residuals. Residuals there, that's a residual. And it looks at each residual and it squares that residual and it adds them up 1 through n. Now if you want to rewrite what is the residual is yi hat, or yi rather, I'm sorry, the response minus the fitted value yi minus yi hat squared, and then of course we're summing 1 to n there. And if you want to rewrite this even further, you can, and have the sum of yi minus beta naught hat plus beta 1 hat xi squared. Okay, so what we do, there's some mathematics in the background, is we would use calculus to see what two values here make this overall function the smallest, and calculus can let us do that. We're not going to do that in this course. We're not going to do the actual calculus, but I just want you to be aware of that. So I'm going to make a reference to it. Using calculus, one can show that SS residual is minimized when a couple of things. Beta 1 hat is this quantity SXY over SXX, and beta naught hat is Y bar minus beta 1 hat X bar. And this is, let me define a couple of these things here. This is a sum of squares. This SXY quantity is the sum, I goes from 1 to n, of xi minus x bar times yi minus y bar, and this SXX is the sum of the square deviations in x. Okay, and so the point the point is that these values, these least squares values here, beta 1 hat and beta naught hat, are determined solely by the sample, or by the data. Okay, so thinking back to, what was this method called? This method was called the method of ordinary least squares to find our estimators. It's called least squares. Hopefully you see why, because we are minimizing this function, minimizing it, and what the function involves squared residuals. Okay, so we're minimizing the squared distance between the data and the line across all n, or at least we're adding up those squared distances there and minimizing that function. Okay, but the big takeaway is that here we have these expressions, the least squares estimators, that give us a line of best fit here. Okay. Now, moving along, the other parameter that we want to estimate is the variance of the error terms. The usual estimator for the variance of the error terms is, oh, I've got my notation wrong here. Let me fix that. SE squared, it's determined by the data, and it's the sum of squares residual divided by n minus 2, which would be just the sum of yi minus yi hat squared over n minus 2. And so if you want to look at the scatter plot to see what that is, again, the residual is the distance between the data, the response, and the line, and you square that and add those up, and that gives you SS residual. I do want to say something about, well, you may have the question, well, why did we square this to begin with? We squared it because the line of best fit, as it goes through the data, some residuals are positive and some are negative. In fact, you can look at epsilon 2 hat, it's actually negative. So they actually, if you add all those positives and negative residuals together, they wash each other out. So that sum is always 0. So we square it to take care of that sort of problem. Okay. Now, this is our estimator for the variance. So we have our estimator for the slope for the intercept and the variance in simple linear regression. Now here is our Sparrow data revisited. Now this table here I generated within Excel. Fairly straightforward. This is the original data right here, and then within Excel I took in this third column here, I took each y value and I subtracted off the mean of y minus y bar, and then I squared it. Okay, and the first one was 49. So these are the square deviations in y. And then I did the same thing for x. These are the square deviations in the fourth column for x. And then this fifth column here is x minus x bar times y minus y bar. That's the deviation in x times the deviation in y. And that is all straight from the data. Okay? And this bottom row that I have here is the sum of those across those respective columns there, or summing down the rows rather. And so the sum of the y's is 130, the sum of the x's is 44.2, and so forth. So what I want to do ultimately is this kind of data here, and I want to find the estimates for beta naught and beta 1. So let's see, what do I have just to be complete from Excel? We have the following, that the sum of the square deviations in x, that is this quantity here, is given by 19.66. Also, the sum of the cross deviations, or the sum of the x deviations times the y deviations, say it that way, is 70.8. Alright, and then another thing I'm going to need is x bar and y bar. X bar, x bar is 44.4 divided by 13. If you do that, you should get 3.42, and the sample mean for y, 130 over 13 is 10. Okay, so I have those summary statistics. I can get the values that I need here. So thus, beta 1 hat, which is SXY divided by SXX, or 70.8, divided by 19.66 is 3.6. And the slope estimate, the intercept estimate, beta 1 hat is the slope estimate, beta naught hat is the intercept estimate, y bar minus beta naught hat times x bar. That's going to be 10 minus 3.6 times 3.42, that's x bar there. You do the arithmetic and you get negative 2.312. Okay, so hence our fitted model is y hat, it's the intercept, the negative 2.312, plus the slope 3.6x. That's our fitted model. That's the line of best fit through the data, and you can see that here. I actually used Excel to plot this line through the data, and there, that's the equation for that line. Okay, so that's our fitted model. Now, thinking back, how would we interpret these quantities? How do you interpret the slope estimate? How do you interpret the intercept estimate? It goes back to, how did you interpret these things in a high school algebra class? The slope, if you recall, the slope is the rise over run from your high school math class. And so or another way to think of it was the change in the y over the change in the x. And so what that meant was that if the change in the x, if you force that to be 1, if I force the change in x to be 1, then the slope is simply the change in y. Okay, so what do I have here? I have an estimate for the slope. So this tells me that 3.6 is related to a unit change in x for a overall change in y, or the response. And so if we want to give this some interpretation, let me do that, because that is important here. It would be as follows. We estimate let me back up. I want to write that differently. For a 1 centimeter increase in wing length, we estimate an increase of how many days? Of 3.6 days. Okay, that's our interpretation. That's our interpretation in the model. So if we were a biologist and we saw the wing length, if we saw a sparrow and we saw that one had actually, if we saw 2 sparrows, one was had a wing length that was 1 centimeter longer than the other, then based on our model, we would estimate that the larger sparrow is approximately 3.6 days older than the younger sparrow. Okay. All right. So this here is our motivation for simple linear regression and some basic ideas within it.